Chapter 16, Part 3, we're going to be switching gears here, and instead of looking at discrete random variables, we are going to start talking about continuous random variables. So a continuous random variable is very different from a discrete random variable. We no longer have a list of discrete outcomes with their associated probabilities. Instead, we're going to look at these variables that can take on any value. So it'll be impossible at this point to make one of those probability distribution models where you listed the different outcomes and their probabilities. We cannot do that for continuous random variables. With these continuous random variables, any single value will not have a specific probability. For example, it would be very difficult, impossible, to calculate the probability that a person has a height of exactly 64.67829 inches. That's very, very specific, very precise. It's going to be very difficult to find that exact probability. We've actually seen this idea before when we looked at normal models. We never calculated the exact probability of a z-score being equal to something, right? Like we never found the chances of z being equal to 1.68, but we could calculate the probability of it being lower than a value, above a value, or in between two values. So what's nice is much of what we've learned about discrete random variables is also true for continuous random variables. So all of the things we've learned about so far, like multiplying by a constant, adding or subtracting two different random variables, that stays the exact same for continuous random variables. Okay, so when two continuous random variables have normal models, so does their sum or their difference. So if I was looking at one random variable for height, they told me that followed a normal model, and then I looked at another random variable for weight that follows a normal model. When I either add or subtract sum and weight, height and weight, that will still follow a normal model. So let's go ahead and take a look at what this looks like through an example. Example 1 says, Brooke works at Kohl's and is usually in charge of the fitting rooms, which requires rehanging clothes and sanitizing the rooms. The time required to rehang clothes in one room can be described by a normal model with a mean of 3 minutes and a standard deviation of 0.5 minutes. The times for sanitizing the rooms can also be modeled as normal with a mean of 2 minutes and a standard deviation of 0.25 minutes. Now they are giving us two different random variables here. It looks like we are talking about hanging clothes and also sanitizing. I like to just real quick write out what the mean and the variance are for both of these. So the first thing we were doing is talking about rehanging clothes. I'm going to call that R. You could pick any capital letter there. My expected value for rehanging the clothes, or my mean, was 3 minutes. They told me the standard deviation. As we've seen, we're most likely going to be working with variance first. So I'm going to find the variance of rehanging clothes by taking that standard deviation and squaring it. The other random variable we were looking at was sanitizing rooms. Still telling us that it's normal. So my mean for sanitizing rooms, I'm going to use S for that one, is 2. And again, I can find the variance by squaring the standard deviation. Okay, part A says, what is the probability that sanitizing 2 rooms takes over 5 minutes? Now, the first thing I need to do is think about whether this is a continuous or a discrete random variable. We're talking about time in this case. Time is something that we would measure. We wouldn't be able to count. If I'm just thinking in general, I mean, it could take Brooke 1 minute, it could take her 1.2 minutes, it could take her 1.21497 minutes. There's no way I can make one of those probability charts. So this is going to be a continuous random variable. Now, because I know it's continuous, I am eventually going to want to make one of those little normal models. Okay, now there's two things that I need for a normal model. I need a mean or an average. I'm going to use mu there. And I also need a standard deviation. This should be the first thing that we always find, is that mean and standard deviation. Now we're looking at sanitizing 2 rooms. So I'm not going to be using this R for rehanging clothes. I'm just looking at sanitizing, and I'm actually going to be sanitizing 2 rooms. So I'm going to start with finding the expected value of sanitizing 1 room, so I'm going to use S1, plus sanitizing another room, so I'm going to call that S2. Now we've learned with our random variables that when I'm finding the expected value of 2 random variables being added together, I can just take each of their averages and add them. So sanitizing 1 room took an average of 2 minutes. I'm doing 2 plus 2, which gives me 4. Okay, next up we're going to find the variance. Still working with S1 plus S2. My variance over here was 0.0625, so I'm going to add that again. Which gives me a total of 0.125. From here, I want to find the standard deviation. To find the standard deviation, once we have the variance, we're just going to square root this piece. So I'm going to square root my variance, and that gives me, if I round here, I'm going to just round to 0.35. Okay, at this point we have now found our mean and our standard deviation. Those are the 2 things that I need in order to create this normal model. So I'm going to draw my normal model. I'm going to label my mean or my average of 4 minutes. So that's on average how long it would take to sanitize 2 rooms. The standard deviation is 0.35 minutes. Okay, at this time, now that I have my normal model, I can look at what the question is actually asking. I'm looking for the probability that the sanitizing of 2 rooms takes over 5 minutes. So based on my normal model here, I would have 5 up to this side, and I'm looking for over 5 minutes, so my shading would come over here. The rest of this problem is solved using everything that we know about normal models. So I'm going to take this 5 and convert it to a z-score. So I would have 5 minus 4 dividing by 0.35. I'm going to go through this part with the normal models pretty quickly because we did spend some time last class reviewing that normal model. So I get a z-score of 2.86. From here, I'm going to use my calculator. I'm going to be using normal CDF because I'm looking for a percentage. So that's second vars going down to normal CDF. My lower bound should be this z-score that we just found, so the 2.86. My upper bound is going to be just a very large number because my shading goes all the way to the right-hand side there. Mean and standard deviation are staying the same. And we get an answer of 0.0021. You could leave it just like this. You could also change it into a percentage if you want. This would be 0.21%. So based on the information that we are given, there's a very, very low chance, a 0.21% chance, that it takes Brooke over 5 minutes to sanitize 2 rooms. Part B says, what percentage of the fitting rooms take longer to sanitize than to rehang? So I'm looking at what are the chances that it takes Brooke longer to sanitize. So if I'm thinking about my random variables, I'm using S. It takes her longer to do that than to rehang. So my sanitizing needs to be greater than rehanging. Now at this point, I have my two random variables. They're not really connected though, like my last ones were connected by addition. So I want to try and get these random variables over to just one side. So I'm going to subtract this random variable r, then I would have s minus r is greater than 0. This is what I'm going to be focusing on. I'm looking for the chances that when I take my sanitizing and subtract the rehanging, it's something greater than 0, which means that the sanitizing took longer. Now, you could have done this another way, so there is another option here. If you decided to subtract the s over, you would then be looking for r minus s less than 0. These do mean the same thing. So you can use either one. I'm going to focus on this one over here for this problem. Again, this is a continuous random variable, so I need to re-find a mean and a standard deviation for the subtraction of the random variables. So let's start with our expected value. I'm going to find s minus r. So I'm taking the expected time for sanitizing, which was 2, and subtracting r, which was 3. That gives me -1. It is okay to have a mean of -1, or of the negative. Don't freak out if you do get a negative there. From here, we'll find the variance. Remember that variances are tricky. Even when we're subtracting, we always add. So I'm going to take my variance for sanitizing, which was the 0.0625, add to the variance of rehanging, which is 0.25. I think that right there is kind of the hardest part, is remembering that your variances always add. So I got 0.3125. I do want to then square root that to get my standard deviation. So rounding, I'm going to do 0.56. So far, I know now that I can draw my normal model here. We just found a mean or an average of -1, a standard deviation of 0.56. Once I have my mean and my standard deviation, I have my normal model. From here, we want to think about where I would drop down, right? Like the last one, we looked at 5 and we drew our little drop down at 5 and then shaded accordingly. From here, it's kind of tricky when you're looking at which one's longer than the other. We're going to go back to the starred area, and we're looking for where this difference is greater than 0. So 0 is going to be my drop down. So if -1's over here, 0 would be a little bit this way. I'm looking for greater than 0, so I'm going to shade to the right. Again, same thing here, using what we know about normal models. I'm going to start with converting 0 into a z-score. A little bit tricky here with that -1 being your average. It does change this into a plus. We should get 1.79 as our z-score. Once I have my z-score, again, I'm going to be using normal CDF. My lower bound is the 1.79. That's where my shading began. My upper bound is a very large number. So my calculator, second bars, normal CDF, starting at 1.79, ending just very, very large. And we get 0.0367 or 3.67%. There's about a 4% chance that it will take Brooke longer to clean a room than it will to rehang clothes in that room. I do think these problems involve a lot of work, especially this first part here. This part's very, very important when you're finding that mean and standard deviation. Please keep in mind though that the AP graders and myself as well, we snowball grade on this type of question. So if you made a mistake, like you forgot that variance is add, so you subtracted here, technically everything you do with that normal model is going to be incorrect, but you would still get full credit provided that you're showing all of your work. Please don't try to skip steps here. We want to see everything that's on here. Show me your work for mean, show me your work for that variance and standard deviation. You absolutely need a picture, your z-score, and then your percentage. Let's take a look at a few more examples on the next page. All right, example 2. Ethan's favorite food is ice cream. The amount of food that Ethan can pour into a small bowl varies with a mean of 1.5 ounces and a standard deviation of 0.3. So first variable I'm noticing is the small bowl. I'm going to use an S to represent that small bowl. So my expected value for the small bowl is 1.5 ounces. And the variance for the small bowl, I'm going to take that 0.3 and square it. We get 0.09. So that's all for the small bowl. A large bowl holds a mean of 2.5 ounces with a standard deviation of 0.4. So now we're looking at a large bowl. So I'm going to use L there. My average was 2.5, and my variance, again, we can find by taking that 0.4 and squaring it. Okay, Ethan opens up a brand new container of ice cream. He's going to scoop ice cream into one large bowl and one small bowl. I don't know if he's sharing. It's his favorite food, so I'm going to guess that he's just eating both. He's eating a large bowl of ice cream and then a small bowl. In part A, we want to figure out how much more ice cream we expect to be in the large bowl. So what do we expect to happen? That means we're looking for expected value. I'm looking for large compared to small, so I'm going to take large and subtract the small. Expected values, just subtract, so I would take my 2.5, subtract 1.5, and I'm left with 1. So I'm expecting about a 1 ounce difference, 1 ounce more of ice cream in the large bowl. Part B is asking for the standard deviation of this difference. So we're going to start with finding our variance. Still using large minus small. So my large variance was 0.16. Remember, variances always add. My variance for small was 0.09. That should give me 0.25. Once I have that variance, to find my standard deviation, we simply square root it. Square root of 0.25 should just be 0.5. Okay, part C says, if the difference follows a normal model, what is the probability the large bowl contains more ice cream than the small bowl? So I'm looking for large bowl being greater than small bowl. Now we did say that technically you could subtract either way here. It looks like we already have the expected value and the standard deviation for L minus S, the large minus small. So I would try to keep that consistent here. So if I were to subtract this small bowl over, I would get L minus S is greater than 0. This is the one that I'm going to use because that L minus S, we already have the mean and standard deviation. So if I draw my normal model here, my mean, my average, we just found to be 1 ounce. Standard deviation was 0.5. I'm looking for where this is greater than 0. So 0 is going to be way over here, and we're looking for greater than. Again, I'd start with converting that 0 into a z-score. Gives me -2. From there, I'm using my normal CDF again. Starting at -2, ending at just a very large number. Mean and standard deviation will stay the same. So second bars go into my normal CDF, -2 to a large number, gives me 0.9772 or 97.72%. So there is a very high chance that when Ethan scoops his bowls of ice cream, he will get more ice cream in the large bowl than the small one. Okay, part D says the amount of ice cream the manufacturer puts in a container is a random variable with a mean of 16.3 ounces and a standard deviation of 0.2 ounces. So at this point, they're introducing a new random variable. They're talking about the container of ice cream. So I'm going to use C here. The expected value for that container is 16.3. Variance is 0.2 squared. Says if you pour a large bowl and a small bowl, find the expected amount of cereal left in the box. That should say container. Assuming it's not a box of ice cream. And find the standard deviation. So if Ethan opens up this new container of ice cream and he scoops out his large bowl, scoops out his small bowl, what do we expect to be left over? So this is a little bit tricky. What we're actually doing here is combining 3 different random variables. So I'm starting with the container of ice cream. He's subtracting a large bowl and he's subtracting a small bowl of ice cream. So expected value, I'm just going to take each one of them and subtract. So my mean was 1.5 and 2.5. So I'm expecting 12.3 ounces to be left over after he pours the large and the small. Variance, again, I'm looking for the container minus large minus small, but remember that variances always add. So I'm going to take the variance for that large container, add it to the variance of the large, 0.16, and the small, 0.09, and if you add those in a different order, that's totally fine. We're just adding, so order doesn't matter here. So I get 0.29 as my variance. And standard deviation, I'm just going to square root that. Calculator today. 0.544. That's standard deviation. A little bit trickier there using the 3 random variables, but all of the rules that we've seen with those random variables do stay the same. All right, we have one last example here, example 3. Ari spends a lot of her time creating crochet blankets, which sounds super cozy to me. She can create 2 sizes of blankets, a small blanket and a large blanket. The small blankets cost $40. This should say $40 per day to make. So that's including the material and Ari's time. I mean, her time is very valuable, so small blankets cost her about $40 per day to make. It takes her an average of 3 days to create these small blankets with a standard deviation of 0.8 days. The large blanket costs $60. Again, this should say per day to make, and they take Ari an average of 6 days to create with a standard deviation of 0.2 days. Okay, the two random variables we're looking at here are the small blankets and the large blankets. So I'm going to use S for small and L for large. Very creative there, right? So my expected value for that small, I'm expecting it to take her 3 days. And let's find the variance for small by taking 0.8 and squaring it. Expected value for the large blanket is 6 days with a variance of 0.8, 0.8 again? Oh, 0.2. 0.2, so 0.04. Okay, we are looking for the mean and standard deviation of the total cost for creating both blankets. So what's tricky about this one is the expected value and the variance, the random variables that were given were all in days. This was the average number of days that it took, but we're looking for the cost. So we're going to have to get these costs involved, the $40 and the $60. When I go to find that expected value, instead of just using S, in order to get the cost involved, I'm going to multiply by the cost. So it cost her $40 for each of those small blankets. So I'm going to do 40S. And I'm looking for total cost, so I'm going to add it to the 60 large. Okay, so I'm going to do 40 times S, which was 3, plus 60 times 6. So $480 is the total cost for creating both blankets. That's a very expensive blanket, so I don't know what kind of crocheting Ari's doing, but it's costly. Let's go ahead and find the variance. Still doing 40S plus the 60L, so it's for that cost. Okay, remember here that when we have that constant that's being multiplied and I'm finding the variance, I need to make sure that that is squared. So I'm going to do 40 squared times the variance for S, so the 0.64, plus the 60, which is a constant, so it's squared, times the variance for L, we get 1,168. From here, to find that standard deviation, we are going to square root. We get $34.18. So we expect Ari, if she's creating both blankets, it's going to cost her $480, and that standard deviation will be 34.18. Be careful, there are quite a few problems that you'll see where they give you a random variable that's in days or hours or weeks, something like that, but then they ask you for the cost. So make sure you always multiply the cost with that random variable.